As Dave mentioned, the title Light-Matter Interactions, and that's the focus really of a new program, a new Energy Frontier Research Center at Caltech, as I'll describe in a moment. And we think there's a really interesting opportunity in solar energy conversion to look at new designs and new ideas in the non-electronic part of the solar energy conversion, namely light capture, light absorption, light focusing, and so forth. And I'm going to talk about some photovoltaic fundamentals, some sort of set the landscape for those of you who are not only casual observers of the solar energy scene. And I'll say a little bit about fundamentals of solar cells and light trapping. Then I'm going to describe two new kinds of solar cells that we've been involved in making. One is called wire array solar cells that are dense arrays of upright wires, and plasmonic solar cells where we use metal particles and metal thin films to scatter light into modes that enhance the absorption relative to bulk sheet materials. And then I'll say something at the end about looking over the horizon at currently impractical but very interesting and maybe someday practical materials, optical metamaterials that have the opportunity to control dispersion of light in materials in interesting ways that may be of use for photovoltaics in the future. And the work is enabled by a talented group of students and postdocs at Caltech. And I'll call out also some senior collaborators, Albert Polman, who is a group leader at the FOM Institute in Amsterdam. Has been a longtime collaborator of mine. So the backdrop to my first slide here, I think, is probably something that is relevant, very relevant for your EFRC here as well, because it's a light emission map of the Earth. And those of you here who aspire to transforming lighting with solid-state lighting, or should be apprised of this if you're not already. And it really is an illustration of how global, how vast the scale of energy consumption is and how global it is. It is, you can see, somewhat inhomogeneously distributed. Look how dark this is right here, or here, or here, even in places where we have dense populations. And of course, there are some places where they're half bright, like here and here, where the brightness is changing rapidly. And the reason for this, of course, is because light emission is a proxy for electricity use, which is itself a proxy for energy use, or proportional to overall energy use. And if you consult the International Energy Agency or the United Nations, they will tell you that there's a direct correlation between energy consumption per capita and per capita GDP, or what the UN terms Human Development Index. So there's a direct proportion between energy consumption in your life and your quality of life. So as a dramatic example, this notice here that in East Asia, this is Eastern China, Japan. Here's South Korea, and this dark portion above South Korea here is North Korea. So that's an illustration. You can see dramatically geopolitical consequences here directly by looking at the world at night.
So, Harry, I might point out, when Steve Kuhn is here, he pointed out that obesity was also correlated with GDP. So you personally are looking rather poor.
I see. Okay. Well, so that's why energy efficiency is so important here at Santa Barbara, that we should need human energy efficiency as well as energy efficiency for lighting, right? Okay. So, and I think the thing that has really been striking in the last few years is that we've, I think, forged a broad societal consensus. Whether you are a conservative that cares more about security, or whether you're a liberal and care more about climate change, the answer is yes. We need to radically transform our consumption patterns and energy supply mix so that we create a sustainable and secure future. And so there's broad consensus across the political spectrum that that's important. Okay, so here we are at the moment. We're essentially living in a world. This is a little bit dated, but the purpose of this was dramatic to show that in the recent past, solar was having an absolutely insignificant, still has a relatively almost insignificant impact on overall global energy use. And that really illustrates the scale of energy use over between about 86%, 88% of our total energy consumption in the world comes from fossil fuels at the moment. And If we simply forge into the future with a business as usual approach to energy production and consumption, that is unlikely to change. And you can see here the numbers are enormous. So to give you a scale for the numbers, the instantaneous burn rate of the Earth right now is 17 terawatts. So that's a unit even for scientists, which is hard to fathom. So to give you an idea, some of you may have gotten up this morning and dried your hair with a hairdryer. Anybody do that this morning? Yeah. So one person here. I guess it's pretty dry in Santa Barbara. You don't have to do that. But suppose you did. That's about a 1 kilowatt appliance. So the way to think about this is that all the time we have on Earth the equivalent energy use of 17 billion hairdryers running all the time, or roughly 3 hairdryers per human on Earth running all the time. And of course you're a disproportionate energy consumer, so you have more than your fair share of hairdryers going on all the time. And that's the thing so the scale is staggering, the scale of energy use. And that means to have an impact on energy supply, we have to be thinking at the terawatt scale. It's not enough to have an interesting little technology that will make megawatts or gigawatts. Doesn't matter on the global scale. You have to think about terawatts. So the other exciting feature about photovoltaics is that we are currently close to a tipping point, where there has been a widespread perception and for the recent past and present truth that photovoltaics is too expensive relative to other competitive forms of energy, whether they be fossil fuels or wind. But photovoltaics, depending on the electricity price that you pay, is somewhere between a factor of 2 and 3, maybe as high as a factor of 4 for cheap electricity, too expensive at the moment on a levelized cost of electricity basis, in other words, averaged over the year. And we're inexorably pushing down. So 20 years ago, we were living in a world where we were off by a factor of 10 relative to grid parity for electricity for residential and commercial use, or here for utility generation. This is about, for those of you in back, that's about 15 cents a kilowatt hour and about 7 cents a kilowatt hour for utilities. A coal plant flat out running in the middle of the night selling to the lowest cost customer is about a nickel a kilowatt hour. But you can see here, we're sometime in the next decade, it's uncertain exactly what the time scale will be, we will reach the point where photovoltaics will be at grid parity with residential electricity prices. In fact, I encourage you to all go home and read your utility bills, your electric bill. You pay a tiered electric rate depending on your consumption, and the last amount of consumption you have every month is the most expensive. And in the summertime, if you're a Californian, that rate is typically way above this number. I pay a rate, and I have a relatively energy efficient house, somewhere in the range of 25 to 30 cents a kilowatt hour for the marginal electricity when the consumption is highest in the summertime, when people are running air conditioners and so forth. So there are some times already where photovoltaics is favorable, and this is an indication of where it is on an annualized average basis. So that's a reason why virtually every large multinational large company in the world is investing in and developing research programs. Even IBM and Hewlett-Packard and so forth, Intel are working in solar energy because they're all aware of this trend. So the other reason why we're interested in photovoltaics is because the solar resource is enormous. This is from GSEP. It's a very busy plot showing the energy flows into the surface of the Earth and the reservoirs of energy that we have. And I don't have time to go through the whole thing. It's a very interesting plot that you can download from Stanford. But you can see here that a substantial fraction of the total energy input to the Earth comes to the surface as solar energy. So it's an enormous resource compared to all of our other either conventional or renewable sources of energy. It's not being tapped at nearly the potential that we could exploit. So if I were to plot, roughly speaking, and compare this resource in sort of, imagine the resource was represented by spheres of these equivalent volumes here. This depicts the solar resource that we would have. This is the amount of light impinging on the Earth's surface, and this is some conservative fraction of this land area that would be potentially available for use for photovoltaics. And it vastly exceeds our consumption. So that's the main point I wanted to make, is that the solar resource is enormous. There's no limit to it compared to to global consumption. And in fact, it's much larger than the resources we have for other renewable sources of energy, which are comparable to, you can argue about these as to how much is the available resource, what fraction and what fraction is available at what price and so forth for geothermal, wind, and biomass and so forth. But clearly, there's no argument that there's plenty of solar energy. Even in the cloudiest place in the United States, in the northernmost stretches of Vermont, or in Germany. In fact, the world's largest solar market at the moment is in Germany, where it's much cloudier than it is here in Santa Barbara. So solar energy can be a supply source everywhere on Earth. So what about land area? Would land area be a limitation for the use of solar energy? And this shows an indication, it's a very gross estimate of the land area that would be required for generation of all US electricity. Suppose we built a compact photovoltaic array with 10% efficient modules here between, so maybe you're a little bit nervous if you live in Albuquerque or Phoenix and you see this plot. But of course, solar energy would never be built in this way. It would be built in a distributed manner, or at least photovoltaics. But the point of this plot is to show that while this is a large amount of land, it's not a ridiculously large amount of land compared to the US land area. So you can do make a similar plot for, imagine you grant me the conceit that I have some method for unity conversion efficiency, interconversion between solar generated electricity and other forms of usable energy in the United States, transportation fuels, industrial heating, energy for industry. So that's obviously an overestimate, but it's not an overestimate by more than a factor of 3 or 4 or something like that. But you can see this is the box that I would need. It's about 10,000 square miles to generate all of US primary energy from solar energy. So again, that's a big amount of land. And now you're definitely nervous if you're living in Albuquerque on this chart. But to give you an idea, this is solar would be distributed. And this is comparable to the land area that we have already allocated for roads and utility rights of way in the United States. It's about 4% of the land area of the continental United States. So to give you a scale of the photovoltaic deployment to essentially reach into a substantial fraction of US primary energy, imagine we were to put photovoltaic arrays along the medians of divided highways and in existing utility rights of way. And you get about the right sense of scale for deployment of solar energy. So land area is not a limitation. By the way, this is very different from the recently, I think, adjudicated in the public sphere debate about fermentation of plant matter for biofuels, where it's clear that with more than the available US arable land area, we could not produce enough fuel to fuel the US fleet. So that's an example where the scaling just doesn't work. So if you ask Chris Somerville at the Energy Biosciences Institute in Berkeley, which is working on this, he'll tell you that the maximum we could reach, say, in the United States would be, say, 20% of US transportation fuels. So that's, in contrast, photovoltaics, because of the conversion efficiency and the solar resource, really does represent a major source of energy generation. Of course, there are problems to deal with intermittency of photovoltaics. The sun is predictably intermittent. It goes away every night. And we have to have opportunities and options for storage. But this gives you an idea that the scale can be very significant. What about materials? Is there a inherent material limit? We said that solar resource is not a limit. Land is not a limit. What could materials possibly be a limit? One way to view this and frame the question is to look at the periodic table not in the conventional Mendeleev periodic table form, but in a way that a geologist would look at it. And this is a plot, for those of you in back, this is a plot scanning 15 orders of magnitude in relative abundance of these elements in the Earth's crust as a function of atomic number. And this, of course, comes from the fusion cycle in the sun, this distribution of elements. We're essentially all star matter, and the composition of elements on the Earth that was available as a function of atomic number is highly unequal, with the heavy elements being much less abundant. So imagine we wanted to construct a terawatt of photovoltaics with optically thick cells at, say, 15% efficiency. Roughly speaking, this dotted line represents the line of demarcation between elements that are abundant enough in the Earth's crust and those that are not abundant enough to scale to produce a terawatt of solar electric energy by photovoltaics. So now let's look at the photovoltaic thin film materials that are currently being commercialized in the marketplace. Copper indium gallium diselenide, cadmium telluride. You can see here the largest US photovoltaics company is First Solar. Their technology is polycrystalline cadmium telluride thin films. Tellurium is one of the rarest elements in the Earth's crust, and it simply will not scale. And this is certainly, no doubt, not escaped the notice of people at First Solar, and I'm sure, in fact, I know they're busy looking at other materials. And this is the reason why. And this is a serious problem for terawatt scale. You know, it's a good business. You can make a few tens of gigawatts of photovoltaics and perhaps pay back your venture investment in a technology, but it's not something that's scalable. So silicon, of course, is very abundant, and that's a good favorable point for silicon. The current wafer-based silicon technology that we have for photovoltaics is too expensive, though. And that is why the thin films of these rare materials are growing in their manufacturing capacity at a faster rate than wafer-based silicon, because the cost per watt is significantly lower, even though we're eventually going to run out of these materials and the cost will go up, and somehow there will be a threshold that we will where we'll be limited by material availability. So one way we might innovate our way out of this conundrum would be to make photovoltaic materials that are essentially mineral-like semiconductors. You might imagine looking at compounds like copper oxide, zinc phosphide, iron disulfide, iron oxide, things that rocks and rust and things that you find in the desert. But of course, we don't normally think about these as electronic materials, and the reason we don't is because these haven't, years and decades of investment haven't been made in the purification and crystal growth of these materials that many of which exist as useful semiconductors. We don't know a lot about their doping properties. There hasn't been a technological incentive to develop these materials, but there are a number of semiconductor materials that you can imagine making with transition metal oxides, phosphides, sulfides, nitrides that would certainly satisfy the criterion of being abundant enough. Notice, for those of you who are compound semiconductor people, that gallium arsenide actually is above the bar for a terawatt. That's good news for you if we work on 3.5s. Indium gallium arsenide and indium gallium nitride is a problem. The other reaction you might have to this this materials picture is to say, could I potentially make photovoltaic modules and cells using less material? This would, of course, be desirable in any case because you would lower the cost and simplify the manufacturing and so forth. So is there a way that I could dramatically reduce the thickness of a material, the total volume I would need? And I could do this if I had some method for enhancing the light absorption or light trapping in a material. And that's really been the focus of one of the core focal points of our research and the work of our Energy Frontier Research Center. And I'll tell you a little bit more about that. So really what we're interested in is this whole field of artificial photonic materials, which is now about 20 to 25 years old, which began with the advent of so-called photonic crystals, where ordered patterns of dielectrics enabled dispersion of light. So if you imagine you have light coming in as a plane wave from the sun, it has a linear dispersion relationship in free space, and we have some artificial material that can induce dispersion. It can reduce the group velocity of light, slow down the light in the material. In fact, you can do strange things like make the group velocity and phase velocity go in the opposite direction and so forth. We know how to do this. We can do this with metamaterials, with photonic crystals, with plasmonic materials. So the question is, can we do this in interesting ways to the benefit of light absorption for solar energy conversion? So that's sort of a way to frame the science opportunity that we see before us in looking at the optical properties of photovoltaic materials. So this is the sort of premise behind our Energy Frontier Research Center, which is centered at Caltech and which includes significant teams at Lawrence Berkeley Labs and at University of Illinois. And here we're getting a little bit of help in the lab from the Secretary of Energy in some of our work. So if we think about photovoltaic absorbers, what do we require? What are the optical requirements of a photovoltaic absorber? Well, to the great disappointment of many of my students, the sun is not a laser. So it is not a coherent, monochromatic, well-defined, low divergence source of photons. Actually, its divergence angle is not, it's not too bad. If you have direct sunlight, the sun comes from sunlight comes from a narrow solid angle of the sun's disk. But of course, the problem is that it doesn't stay put. It keeps moving. It moves from morning to night. So we can't simply use a simple grating as a way to couple light in, the way you could use to couple light in from free space into a waveguide on a chip or something like that, because of course the sun is a broad spectrum. It's nearly a black body, filtered by atmospheric absorption here of different molecular species in the upper atmosphere. And of course, if it gets cloudy, the thing that happens is that the sun is scattered by clouds, and so then the incident solid angle of the solar irradiance is broad all the time. This is called global illumination. So we have to be able to make solar cells that can cope with the optical requirements of these broad spectral irradiance, changing position of the sun. One way you can cope with this, if you insist on having always the same incidence angle, is to track along with the sun mechanically, but we don't want to do that. We'd like to fix the photovoltaics and have them be flat plates and just simply have them be able to respond and couple light in it over broad incidence angles. Of course, a solar cell is really has two jobs in life. It has to absorb the light, and it has to extract the photoexcited carriers into an external circuit, which then does work on some external load. And so there's some internal source of a dipole field. There are various ways to make this dipole field that produces the charge separation. And so we have to have a cell whose physical thickness is thick enough to absorb the light, and whose physical thickness is thin enough that the photoexcited charge carriers make it to the external circuit or make it to the charge separating junction. So that's basically what we need. And in fact, almost all of the cost, technology development, and all of the paths that we've used for materials development are guided by these constraints in photovoltaics. So if we think about the limits, efficiency limits for a solar cell, these were defined by Shockley, who gave us semiconductor physics in the foundations of semiconductor physics, and Hans Joachim Queisser in 1961, looking at using a detailed balance between absorption and emission of sunlight in a black body. And they first postulated, this is a sort of physicist conceit, that the sun comes from all around you and your cell is at 0 Kelvin. Of course, no real solar cell is like this, but this is a perfectly absorbing black body that can absorb from all of the electromagnetic modes that are available from a surrounding source. A real solar cell, of course, has a finite solid angle from the disk of the sun, and it operates at room temperature. But in any case, once you remove all of the non-ideal conversion efficiency factors by materials purification and device design and so forth, the one limit to conversion efficiency of the charge carriers from the incident photons that you're left with is the fact that you have radiative recombination. So some of the carriers emit light that is then emitted back into free space. So the fundamental limit to a solar cell's conversion efficiency and the radiative recombination limit is that it is also parasitically an LED. And so we would like to be able to trap the light in such a solar cell. But this is really a pretty fundamental limit, and it allows you to define the limits to conversion efficiency for everything else being ideal. The other thing that is kind of interesting that defines an efficiency limit for a solar cell is the how much of the bandgap energy, so we absorb light across a bandgap in the semiconductor, how much of it is available to us as a separated charge potential in the external circuit. If we were at 0 Kelvin, in principle, we could separate an electron-hole pair across the junction, and we would have the entire bandgap's worth of voltage. However, and this is something that people often overlook, photons that interact with materials by light absorption and then spontaneous emission, which is what happens, the radiative emission and the radiative recombination, produce an entropy change, an entropy increase in the photon energy. So light comes in from free space in a well-defined electromagnetic mode. generates carriers. Those carriers spontaneously recombine and give rise to spontaneous emission. But that emitted photon now doesn't go back into the same mode that the incident photon came from. It goes into 4 pi. It goes into any available electromagnetic mode. And that produces an increase in the entropy, if we think about the free energy of the photon. So the open circuit voltage that's available to me is actually equal to the increase in the number of configurations of the emitted photon, which at room temperature is close to 300 millivolts. That's a significant energy loss of the incident photon that you can't do anything about because it's thermal as long as you have spontaneous emission. And that offset is well observed. So this is a variety of different semiconductor materials looking at the band gap. This is band gap here versus open circuit voltage, and this is the band gap versus band gap. So that's a plot with unity slope here, and this is the offset. And you can see for many semiconductors whose band gaps are between 0.7 and over 2 eV, there's a consistent. It's actually more like about 400 millivolts because there are other non-idealities that come into play. Difference between the band gap energy and the extractable open circuit voltage. And by the way, one of the things that dictates is that it doesn't make sense to make solar cells whose band gaps are substantially below about 0.8 eV or so, because the extractable open circuit voltage is way down here, just a couple hundred millivolts. So fundamentals really end up determining a lot of the operational conditions of even the most ideal materials. So solar cells were developed shortly upon the invention of the PN junction and the transistor, also at Bell Labs. Within a few months, they had gotten to efficiencies of 3 or 4%, and within a year, they had gotten over 10% actually with silicon solar cells. Quite an impressive achievement. And this is a busy plot that many of you are familiar with, showing the time variation in photovoltaic conversion efficiency for essentially all of the technologies that have received significant interest. And I'll just point out a couple of curves here. Number one, here's the organics down here. You can see all these curves are essentially displaced in time. But the organics are substantially lower in efficiency. Actually, this is a dated number. I've seen now cells in the literature and preprints that are in the 7% range, even a little more. Another plot here showing for crystalline silicon. This is right here. Conventional crystalline silicon. The last record efficiency was set in 1998. And that tells you that basically we've harvested what device physics and solid-state physics have given us from homogeneous single-junction silicon cells in terms of efficiency. And commercially, we're approaching this efficiency of just under 25%. What's quite exciting here is to see that the multi-junction solar cells have been increasing their efficiency, and now record efficiencies are over 40%. In fact, the most recent record from the Fraunhofer Institute is 41.1% for heterostructure solar cells, multi-junction solar cells. But all of these curves have a common feature. They increase slowly with time, and then they seem to have plateaued for many of them. So we're interested, and these are essentially increases in efficiency that are coming from better semiconductor device design. And we're interested in looking at increases in efficiency and absorption efficiency that come from optical design. So for example, in a multi-junction solar cell, we harvest the excess carrier energy that would otherwise be lost in a single junction solar cell. For example, in a single junction solar cell where I have a single energy gap, photons of exactly band gap energy can be converted at their maximum conversion efficiency. So right here at the band edge, we have the highest extractable power as a fraction of the incident power density in the solar spectrum. For bluer photons over here, there's essentially a quantum defect. There's a difference between the photon energy and the band gap energy that's due to the relaxation, the thermalization of carriers by electron-phonon scattering down to the band edge in the solar cell. It's very difficult, if not, so far it's been effectively impossible to harvest these hot photogenerated carriers before they relax to the band edges. And as a result, over here, there's a big deficit between the power density in the solar spectrum and the converted power. And of course, there's a whole spectrum below the band gap where the semiconductor is transparent that we don't absorb at all. So in multi-junction solar cells, we have this opportunity to both cover more of the solar spectrum and harvest a greater fraction of the power in the solar spectrum because of the smaller quantum defect per absorber layer that exists between the photon energy that's absorbed in that layer and the bandgap energy. And that's responsible for this big efficiency increase. Here are some examples of, these are multi-junction solar cells that are made on silicon in our lab. And these are experimental results for the top two cells here, a gallium arsenide, gallium phosphide cell. And these are made by a process where we start with a silicon wafer, we peel off germanium in a thin single crystal film, transfer it onto a silicon wafer, then grow on this germanium template on silicon, gallium arsenide, gallium phosphide solar cells. This shows the cell conversion efficiency, and there's a little bit of a difference in the open circuit voltage of the cells. But basically, the message is that these are comparable in efficiency to cells grown on bulk germanium substrates. And this is actually a fairly significant feature because a lot of the cost of these multi-junction solar cells comes from the expensive substrate. And in this process, we're able to reuse the germanium substrate many times by peeling off these thin layers. Of course, these multi-junction solar cells are expensive at the moment, and they tend to be used in these concentrator receivers where a relatively small and expensive cell can have its cost amortized over a large optical aperture as compared with a flat plate array. So that even a cell that has fabrication costs of, say, thousands of dollars per square meter can, by being able to collect light over a large optical aperture, can have an equivalent flat plate cost of hundreds of dollars per square meter and therefore be competitive with other flat plate absorbers. One of the things that happens is there's a big change in the power density incident on the cell. And that has an effect fundamentally on the efficiency. If I have some fixed recombination process and fixed temperature in the cell, the open circuit voltage of the cell is proportional to the ratio of the photocurrent to the dark current in the cell. And roughly speaking, it's the ratio of the area of the optical aperture to the cell in this concentrator. And this voltage can increase by logarithmically times thermal voltage times the logarithm of this concentration factor. So in a thin film, so this one way to do this optical concentration is to use such a lens or mirror configuration to concentrate light laterally onto a smaller cell. If you could imagine making conceptually starting with a thick flat plate absorber and making it thinner in such a way that you could still absorb all the light, you would be increasing the excitation level in the semiconductor and thereby increasing its open circuit voltage. And if you do this thought experiment, say for a silicon solar cell, this is done by Martin Green a number of years ago, and thin down a silicon solar cell and imagine still conditions where you would still be able to trap all of the light, you could enjoy an efficiency increase here. This is detailed balance ideal efficiencies here from say 29% up to about 35%, and in the bargain make your cell about 100 times thinner. Sounds like a good thing to do, but of course what happens when you make a solar absorber thinner is that it has finite absorption, material absorption. As you make it thinner, it becomes optically thin. Here's an example showing the spectral quantum efficiency for a silicon solar cell. Here for an optically thick 5 millimeter thick layer. And now as I thin it down, you start to see that we start losing the red response around the band edge of the silicon. And in a range of thickness of a few tens of microns, we start taking a big bite out of this spectral quantum efficiency. A lot of the optical power is lost because the cell becomes optically thin. Here, this shows a cell that's 100 nanometers thick, and it's a tiny, the optical power that's absorbed is a tiny fraction of the total incident power. So it looks like this is an issue if you have just single pass absorption, that the material becomes optically thin. So, and in fact, the limits, what were previously imagined limits to this process were defined by Eli Jablonovich a number of years ago, and using a geometrical ray optics model, he posited that imagine you had a sheet of material that's almost dielectric, has low absorption, it's randomly textured on both surfaces, and if you do a detailed balance between the light absorption and light re-emission at this roughened surface, you come to the conclusion that for such a material in the ray optics limit, that the intensity enhancement you could get inside this material, and therefore the absorption enhancement, which is proportional to the intensity, would be about 2 times the refractive index squared, or about a factor of 25, say, for silicon or for gallium arsenide, maybe a little bit more. If you put a perfectly reflecting back reflector, you get another factor of 2, 4n squared, which would be 50. And so the conventional, or this thermodynamically motivated model says that that's the limit. That's essentially how much you can enhance the absorption by, and the way in which you would do it, by randomly texturing the surface of this material. So a couple of years ago, we began work on a type of solar cell we call a wire array solar cell. And this was initially motivated by the idea that for low quality semiconductors where the carrier collection length was small, we could have much more efficient carrier collection in a solar cell by having a radial p-n junction where carriers are collected laterally across the wire radius, even though the absorption is throughout the wire length. So we orthogonalize light absorption and carrier collection. That was the original idea. It turned out in the end we ended up making quite high quality in silicon solar cells, and so we were no longer limited by this collection length, but we started to see some other advantages of this kind of cell. So, and in fact we've shown with some relatively comprehensive device modeling that you can get up into the 17 to 18% range with a cell using not very aggressive technology for fabrication of the cell and geometry and so forth. So we make these wires in arrays by a vapor-liquid solid growth process where a metal catalyst particle seeds the heterogeneous nucleation and growth of a semiconductor wire. And in fact, if you've been to a recent Physical Society meeting or Materials Research Society meeting, there are entire rooms full of people talking about this process of making nanowires. And of course, mostly when they make nanowires, they come out looking like this. They're relatively inhomogeneous in size, in orientation, and distribution. However, if you're careful about it, this is a relatively simple process, and it's a nice one for growing wires. Each one of these wires is a high-quality single crystal. And we're able to form wires in dense arrays by growth on a carefully designed template using these metal catalyst particles. And the uniform wire diameter also gives rise to a uniform wire length, and so we can make large area arrays that are uniform over square centimeters. Here's another example showing an array that's over square centimeters. This is a nice carpet of wires, and if you look at it, it looks just very black because it's not absorbing very much light. Here it's on a silicon substrate. That's the secret here, is we're templating on a single crystal, and you'd say, well, not very much advantage here because you're growing on a wafer. Why didn't you just make your solar cell on a wafer? Why make the wire arrays? Well, it turns out that we can peel these wires off. We embed them in a polymer, and we can peel them off and reuse this substrate. So essentially, this becomes a reusable template, and the wire array can be embedded in a polymer as a flexible sheet. And so we can make something that has the characteristics essentially of just a sheet of just a thin sheet of EVA or PDMS that has a bend radius of curvature of millimeters, and reuse the substrate many times. When we make cells, and if we make single wire cells, if we test cells as single wires, we have to lie them down on a substrate, and we make sort of research style measurements where we make 4-point probe contacts and so forth. And we can make cells here that have open circuit voltages in the range of about 550, 560 millivolts. And with a proper AR coating, we can get up for this configuration to an efficiency of about 9%. Of course, in this lying down configuration, this cell is optically thin, so its photocurrent is much less than the photocurrent you would expect for an optically thick cell. And so if we now take this device performance result and put it in, we calculate what the in an array the proper photocurrent would be for higher absorption you get in an array, then the efficiency that we think we can achieve when these things are all stood up in arrays is comparable to the predictions that were made at the outset of the project. So that's where we are at the moment. So another aspect of this is the question of whether or not when you make a dense array like this, do you in fact absorb all the light? When you look at this array, actually it doesn't turn out to be that dense. If we look down on the substrate, the area of the substrate that we subtend is only 5 to about 15% of the projected area. And So we're interested in determining whether or not there's a substantial light absorption. Is there as much absorption as there would be in a solid substrate? To do the measurements, we use integrating sphere measurements because we're interested in both specular and diffuse measurements. To measure absorption, we measure both reflection and transmission and measure absorption from 1 minus reflection and absorption. And of course, using this lithographically patterned scheme for templating wire growth, we can make patterns in whatever array geometry we like, from ones that have long-range order to intermediate range order, quasi-crystalline order, to short-range order. And these are the diffraction patterns you get from the wires if you shine a laser pointer through them. These are the wires themselves. And these are the integrating sphere measurements of the absorption. And you can see these bright spots here are the, actually this is the transmission. So the red spots here indicate high transmittance or low absorption. So there's a substantial variation in the absorption with angle in both the, say, orthogonal directions that comes from this. So the question then is, can we you can see it quite clearly reflects the symmetry of the wire lattice itself. So you can now ask yourself how much light would be absorbed in a single solar cycle, day-night cycle, if the sun were directly normal, under direct illumination conditions, and we integrate the energy generated in such a cell. And we can see that without the array without a back reflector has a dip in its absorption right when the sun is directly overhead, when you have parallel illumination, because of this enhanced transmission along the wire axis. If we put in some sort of scattering structure, either a Lambertian back reflector or dielectric scattering particles, we can increase, I'm going to skip past this for a moment, increase the absorbance here, and so the mid-visible spectral absorbance is as high as it is for the best quality silicon solar cells. It's about 95%. And these are wire arrays that whose volume fraction equivalent to a wafer of equivalent thickness have 4%. In other words, this is a polymer sheet embedded with wires, parallel array of wires, where the silicon volume is 4%. The wires themselves still have excellent internal quantum efficiency. These are measurements of the internal quantum efficiency made in a photoelectrochemical apparatus. We have similar measurements using transparent conducting oxide contacts. And while the absorbance of this structure fell off because we didn't have the textured back reflector, we can measure the absorbance and the carrier and the photocurrent, and the ratio of which is the internal quantum efficiency. And you can see here, until we get close to the silicon band edge, it's very high. So these are good photovoltaic collecting junctions. When we have a Lambertian back reflector, we find rather interestingly that compared to a specular smooth piece of silicon, we have substantial absorption. But compared to a randomly textured sheet of equivalent thickness, this is the spectral absorption. The randomly textured sheet absorbs slightly better in the mid-visible range. But in the region where silicon has low absorption, we actually have higher absorption in the wire array than we do in the randomly textured sheet. So in some sense, we have exceeded this ergodic limit that was the previously imagined limit in these wire arrays. And a thing to mention is also that the wire arrays have an equivalent volume here of a thin film. So if the wire array has is 100 microns thick and it has a volume concentration of 4%, it's equivalent essentially to, in volume, silicon volume, to a planar film that's 4 microns thick. So let's see, I want to just say a few words about another approach to enhanced light absorption by coupling into surface plasmon modes on the, at metal dielectric interfaces in solar cells. And surface plasmons are essentially polariton waves that propagate along a metal dielectric interface. They're essentially a coupling of the polarization of the charge density in a metal that's illuminated to the electromagnetic field that extends into both the metal and the dielectric. And this wave here, this polariton wave, is a guided mode along the interface. And as we approach the natural frequency for oscillation of electrons in the metal, this wave becomes highly dispersive. The group velocity bends over and becomes very small. The wave slows down, and there's substantially increased absorption. And we can tune this dispersion relation by changing the thickness of the metal and various other characteristics, the dielectric constant of this dielectric, and so forth. So in photovoltaics, we're interested in exploiting the role of plasmonics in two ways, one of which is to use localized metal particles as scatterers to scatter light into dielectric waveguide modes of semiconductor films on low-index substrates. You might think of this like a integrated photonics waveguide, or to scatter into films that are coated on the back surface with a metal film here. And in both cases, we can generate guided modes here that have substantially increased absorption relative to single-pass absorption through a thin sheet. This is an example of just showing a model system of a textured reflector. And this is a modal decomposition in simulation showing the confinement of the surface plasmon polariton mode in a thin film. And this is the silicon photonic, this is several TE optical modes in the same thin silicon film, about a half a micron thick. And so you can see here the modal confinement characteristics are very different depending on the mode. And they have different fractions of absorption in the semiconductor and the metal. One of the things that's interesting about these is that if we corrugate, if we create particle arrays or grooves and bumps on a planar metal surface that are sub-wavelength in character, these sub-wavelength particles act as dipole scatterers. And dipoles have a broad spectral acceptance for excitation. They, in fact, do generate polarized absorption and emission, but it's spectrally broad. And this shows the angle, relative angle independence here of the absorption with just, for example, a single scatterer or an array of scatterers. So indeed, these sub-wavelength scatterers do have the property that they have broad angular acceptance. So then the next thing that we do is to look at the different modes, and different modes have different spectral absorption. And we're interested then in determining what, of all of the modes that are excited in this thin film of semiconductor, what combination of modes and combination of coupling into modes gives rise to the largest photocurrent. And so we can go through on a mode selective basis and determine the incoupling efficiency into different modes, for example, the lowest order TM and TE modes, as a function of the groove height and width and periodicity and so forth. And so essentially what we're doing is we're determining the incoupling efficiency and spectral absorption of these different block modes. These are modes of the periodic structure that exist in this thin film. And these modes that propagate along, this shows the cross-section conceptually of the different mode profiles for the surface plasmon polariton mode, which hugs the interface. Here are TE modes, the lowest order, which is peaked right in the center of the dielectric part of the semiconductor and so forth. And you can see they have different balances of absorption in the metal and the semiconductor. And if you model this as a series of sequential scattering events where light comes in, is scattered from a sub-wavelength scatterer, which is modeled as a dipole, the light scatters into all the available modes, plus some fraction of light also scatters back into free space. It goes along, it's absorbed by exponential absorption in a guided wave mode until it hits another scatterer, and so forth, scatters into other modes, some fraction goes into free space. You can now essentially bookkeep all of the absorption in this thin film. And this shows the enhancement in absorption you can achieve in the semiconductor over single pass absorption. That's on this axis, and this is versus the fraction of light that's absorbed in the semiconductor. So we'd like that fraction to be as close as 1 to 1 as possible, and we'd like to have as large an enhancement over single pass absorption as possible as well. And that indicates, for example, that the SPP, surface plasmon polariton modes, have a modest absorption enhancement, but more worrisome, they have only a small fraction of the light absorbed in the semiconductor. A lot of it's absorbed in the metal. For the other TM modes that are excited, there's a substantial enhancement up to about a factor of 100 in the optically thin region for silicon between 900 and 1100 nanometers, where light is absorbed and a large fraction of it is absorbed in the semiconductor. For the TE modes, you get even a more spectacular increase here, and for proper design can have a very large fraction of the light be absorbed in the semiconductor. And in fact, an exciting finding that Peter Sayeda, who's a sabbatical visitor from Harvey Mudd College, showed last year, for an appropriately designed set of dipole scatterers in a thin film, if you put the dipoles in the right place, they scatter selectively into these modes that have many times the single pass absorption, and you can have modal absorption that beats this ergodic limit. So a carefully designed non-random structure has better absorption than a random structure, and so this is the 4n squared factor of 50 for silicon. And if I put a dipole scatter at some distance from the metal semiconductor interface, say 100 nanometers away in the film, or 250 nanometers away, or close to the surface, I can enhance the absorption in this optically thin region of the cell relative to a randomly textured sheet. So I think that, and now there are a number of examples that show that we can beat this ergodic limit and essentially absorb more light than we thought we could in a thin absorber. So I just want to show you, this is a recent result for a practical amorphous silicon solar cell. Amorphous silicon is one of the thin film technologies that is now in relatively widespread manufacturing for a corrugated set of absorbers made by a nano imprint lithography process and then using a conventional amorphous silicon solar cell fabrication process on top. We're able to show that the photocurrent we get from the periodic back reflector, where we designed for optimal coupling into the block modes that enhance light absorption in the amorphous silicon, we get a larger photocurrent than we could for a purely random back reflector. So this is the standard way in which amorphous silicon solar cells are made, which you coat a randomly textured glass substrate with silver and then zinc oxide, then grow your amorphous silicon solar cell. If instead you make a deliberately periodic pattern, you can get a larger photocurrent. So we don't know, this is not optimized. We don't know if this is the optimal pattern for the highest photocurrent. But we've shown for the first time that this can really exceed what conventional wisdom told us, that a randomly textured light trapping structure was optimal. Now I just want to say a little bit about looking over the horizon at materials such as metamaterials, which are artificial photonic materials that have the characteristic that we can tune both the electric permeability and permittivity to change the real and imaginary parts of the complex refractive index. And this is a whole separate discussion I'm not going to engage in today, but we can make materials whose composite refractive index can be, for example, less than 1, which has very interesting properties, can be 0. By the way, what does refractive index of 0 mean? That means that if you think about the wave vector, k is equal to n omega over c. When n goes to 0, k goes to 0, the wavelength goes to infinity. All of optics becomes quasi-statics, essentially becomes DC circuit theory in a zero index material. You can also achieve negative refractive indices, and these are strange materials. This is an example of a negative refractive index material that we've been working on, a plasmonic coaxial metamaterial. It's a single thin film of silver, about 100 nanometers thick, where we cut air grooves and we can fill them up with dielectric. It helps to fill it with a high dielectric constant dielectric. But these can exhibit for a narrow band of, a band of frequencies in the visible range. It's not narrow, depends on your judgment. It's in the blue-green region. Negative index. Moreover, it exhibits a broad angular acceptance for the negative index mode. Negative refractive index materials have this curious behavior where instead of like a conventional material where we have, by Snell-Descartes reflection, light bent more towards the surface normal and a reduction of the more densely spaced phase fronts in the material. Now we have power flowing from top to bottom incident upon the material, but the phase fronts flow backwards. Light is also refracted to the same side of the surface normal. So for example, just show you, this is one example of this strange material that we're working on. If we have light incident here on the material, this is light coming in at an angle and reflected. Now you can see here the phase fronts are coming in, optical power is flowing down as the amplitude penetrates into the material. But you can see the phase fronts are moving back towards the interface. And in fact, the orientation of the wave coming in is like this, and the orientation of the refracted beam is like this. So this illustrates the opportunities we have for dispersion engineering in relatively simple material. This is just a single thin film of silver that happens to have been made in a somewhat special way. And so it has broad angular acceptance. It has about the same negative index at 60-degree incident as it does at normal incidence. and a number of interesting properties. This is just one example. So if you had such a material, what are some things you could do with it, and how might they relate to solar energy? Here's an example. So for example, if you have a dielectric boundary and light comes in, there's a slight phase slip called the Guss-Hanschen shift that upon reflection represents, it essentially represents the penetration of the evanescent wave into the material. So light, the reflected wave is displaced in phase relative to the incident wave by the essentially the round trip penetration of the wave into the material. So for a positive index, this Guss-Hanschen shift is positive. For a negative index, the Guss-Hanschen shift is actually negative. The wave flips back and comes as reflected back in this way. So now imagine you had a material that had negative index, positive index, negative index, positive index. Then this Guss-Hanschen phase shift would produce a little trapped mode. It essentially produces a resonant mode. And that resonant mode depends on the effective index, which depends on the thickness. And if you taper such a structure, you can show that that acts as a resonant trapped mode whose resonant frequency can be varied along this taper. So now I could imagine making a structure in this tapered negative index material that essentially separates light out into resonant modes that are excited at different depths in these waveguides. And imagine I were to make solar cells in the semiconductor material in each of these layers. I can imagine now splitting the spectrum of incident light into red on top, which is and yellow and green in the middle and blue on the bottom, for example. That's a little bit different from the way you would normally do it. But it's an example of the kind of things you can do with these strange optical materials. So let me just sort of sum up and tell you about some of the things that I described today. One are what we call hyperlight trapping wire array solar cells, which we think is a really new and interesting way. This shows the flexible polymer sheet of making silicon solar cells with a fraction of the material volume with high optical local concentration and absorption that actually exceeds that of the previously imagined absorption limits. I also told you a little bit about plasmonic solar cells, which represent another opportunity for exceeding absorption defined by this ergodic limit in randomly textured sheets. And there are a whole variety, a whole portfolio of possible materials that we can imagine where we essentially sculpt the flow of light through materials by engineering the dispersion to the benefit of light absorption in solar energy and perhaps in many other contexts, in thermal energy conversion, and all manner of ways in which light interacts with materials. So thanks for your attention.
Questions for Harry?
In plasmonics, from what you said, I understand that you use a method to enhance absorption by coupling the incoming radiation into certain Bandgap modes or charge density bases. Are these Bandgap modes charge density themselves constitute photocarrier, or do they couple with the charge carriers in the material to generate the?
Well, so the polarization of the electrons in the metal, those are electrons that stay in the metal. What generates the photocarriers in the semiconductor is the confined EM field, right, in the mode near the surface. So now you have optical intensity that is there, and if it's above the band gap, it generates photocarriers by ordinary absorption. But the main difference relative to light coming in from a plane wave is that now the absorption, the mode is extremely confined in a thin layer. But the photocarrier excitation processes are just the same as they were. It's still silicon, still has the same complex refractive index and same absorption characteristics as a piece of silicon of some other shape would have. Yeah.
Harry, the plot that you showed of the abundance of metals,
Yes.
Was that for the U.S. or worldwide? Because there's quite a difference between the two.
This is it was a relative scale, and it's the relative scale. So it is worldwide. And it's just the distribution
Yeah.
in the Earth's crust. Yeah.
Could you
So-
comment on how that, what the impact, what the implications are for the difference between that for the U.S. and the rest of the world?
Let's see. The story is different for each metal. So.
The rare earths in particular.
Oh, the rare earths in particular. Okay. Well, so there is one mine out in the Mojave Desert between Barstow and Las Vegas, which is the largest mine in the United States. But that mine accounts for something like 13% of U.S. or of world production of rare earths. So we have one place where we can go for neodymium and erbium and so forth in the United States. The world's largest producer of rare earths is in China. So one of the other things that maybe you're hinting at is that the unequal distribution of these rare elements across the globe has geopolitical and geostrategic consequences as well. In fact, our new Energy Institute at Caltech, the Resnick Institute, is going to be hosting a workshop this fall on the strategic implications of renewable materials for renewable energy. How do we design renewable energy systems that aren't, in some sense, held hostage to these rare materials, similar to the way that we are, in some sense, over a barrel, so to speak, with respect to petrochemicals at the moment.
Ben?
So the random texturing gains efficiency. You must lose in the air coating efficiency. What do you do in that case for air coating?
That's a very interesting question. It has a number of answers. So when I texture a surface, that surface itself has a different reflectance from a planar surface that has a optimal planar thin film dielectric AR coating. Okay, I can combine texture plus a dielectric AR coating to further reduce the reflectance of a surface if I choose to do that. Is that what you're getting at, or?
But I would think the efficiency of that AR coating is worse than if you had a planar surface to begin with, isn't it?
Is worse than if I had a.
I mean,
Oh, you mean the relative benefit of having the AR coating?
yeah.
Yes, that's true, but it makes an enormous difference. If I have a high refractive index semiconductor material like silicon or gallium arsenide, no matter what shape it is, having an AR coating dramatically reduces the surface reflectance. Yeah, it's perhaps, in some sense, it's less efficient than it has a less dramatic impact for a textured surface because a planar surface has such a high reflectance to begin with. So,
You're still better off. Okay.
yeah.
Have you used thought about using any of these metamaterials for local field microscopy? It seemed to me there's a potential application there.
So one of the that's a whole different area of interest. But one of the notions of using negative index materials is to use them as lenses, so there are people actively working on making lenses because of this essentially negative refraction means that a slab of that material inherently focuses light. So that's an interesting consequence, and there are a number of groups who are busily working on this. You also have to be careful about the other aspects. For example, there is absorption in these sheets, and you have to think about the consequences of that for your microscope as well. Yeah. Question?
On a few slides before this, you're kind of showing the cost comparison for various forms of energy, like
Yes.
wind and solar. I'm just curious, like I feel like with the utility costs and the residential use, that they're going to factor in maintenance costs into those values. Is that the same? with
Well, okay.
solar?
I think the slide that I showed was from the DOE, and right here, so this is the levelized cost of electricity, which is the cost. That's essentially the cost you pay as a ratepayer, if you're a residential ratepayer or a utility ratepayer. The cost of a photovoltaic system is something that is harder to calculate because usually what happens is you buy this and then you buy it as an investment and you use it for the lifetime, which is warranted lifetime is 25 or 30 years, and you have to find the average cost per watt the energy generated over that lifetime and so forth. But when you do that calculation, all of those same features are incorporated: depreciation, service, reliability, and so forth in both. So I think this is a fair comparison. Yeah.
There's another question. Yeah.
Yeah, you showed an interesting graph showing the flow of energy, and also made an interesting comparison about the amount of land that would be necessary to power, say, the U.S.
Mm-hmm.
I'm just curious if you can make a comment on what you think the effect of covering a very large piece of land with solar absorbers would be. You didn't say reflect the same amount of light.
The albedo problem. You're worried about the albedo. Are we changing the reflectance of the Earth? Okay. So the answer is we've already done that. We've already we've already put down roads and so forth. And if we have efficient photovoltaic devices, they will have a more modest impact on the albedo of the landscape, or the man's altered albedo of the landscape, than, for example, pavement does. Pavement has a very high emissivity, high absorption coefficient, right? So if you're interested in, this is actually, it's a serious question, and it's something you should think about when you think about large-scale deployment of photovoltaics. Are you going to actually induce local warming because you've enhanced the local absorption of the land or something like that? And so I think the answer is that yes, it will have an impact on the local temperature and so forth, but in a way that is perhaps more benign than the ways that we've already done it.
And I guess, as you said, it would be distributed, so it wouldn't be a single large array.
Yeah, that's right. I don't think anybody would want to do it this way. Although when you talk to utilities, they like the idea of doing things in blocks of a few megawatts, because it's big enough to be useful and interesting for them to build, but small enough that they can plug it directly into the grid without building more transmission capacity, specially designed. Yes, well, for present purposes, yeah, I guess. Yeah. So.
Question in the back. Yeah.
This is regarding the plasmon source.
Yes.
Has there been any thought given on the extent of coherence between the polarization of the light and the polarization of the plasmon by itself? So you can define this.
Yeah, we've studied that in quite extensively, actually. So it's an important question, because normally you don't think of the sun as being a coherent light source, right? And you have a laser, you have a spatial coherence length of meters, but it turns out that if you think about just a quote-unquote incoherent black body source, the equivalent coherence length, if you think about it, even for that source, is of the order of a micron or a few microns. So the interaction, so there is actually phase preservation and phase information that is retained so if I imagine light scattering in, coming in, scattering into a mode, and then interacting with the next scatter, which is usually going to be about a micron or less away. That is, to first order, that's a coherent interaction. And so you have to pay attention to the phase coherence. It's not an incoherent process at all. Yeah.
One more. Yeah.
What would the advantage of a plasmon type solar cell versus a photonic crystal type solar cell for scattering bilaterally?
In some sense, they are brethren or sistern, or however you like to say it. They're both dispersive optical materials that couple light into modes and so forth. Every solar cell is going to have a metallic contact to it anyway. And so our strategy was simply to engineer the optical dispersion into that back contact. If you make a photonic crystal, then you typically would have to penetrate the active region of your solar cell, which might have significant consequences for the, you don't have to, but if you did, you either put a dielectric coating on the back or the front, or interspersed in between. So in many ways, they would have very similar functions, and you could potentially design photonic crystal solar cells. But the reason we call this plasmonic photovoltaics, and as we think this is an important concept, is because you're almost always going to have a back reflector there anyway in a thin film solar cell.
It's more of a practical consideration.
I would say so, although it turns out there are also advantages in that metals are much stronger scatterers than dielectrics. So if my goal is to use sub-wavelength scatterers because they have high angular acceptance, by the way, that's a big advantage over a photonic crystal, where a photonic crystal, you don't have typically broad angular acceptance for coupling into a certain mode, right? But if I have nanoscale or sub-wavelength scatterers, if they're made of metals, they're strong scatterers. I scatter light from a large angular acceptance angle, so I can couple light into these guided modes. So it's partly because of a design advantage, and partly because of the reality that your metals are going to be there anyway as a contact, that led us to start thinking about design using patterned metal structures. Yeah.
Okay, Harry has to drive back to Pasadena. Let's thank him for a really. Next week we have Michael Chabanek.